So for this video, I am going to be working out the following exercises from 4.3. So number 13, which is in front of us, and number 18. So with 13, we have relations R1 and R2 on a set A, and we want to give a proof or a counterexample to justify whether the union of R1 and R2 is reflexive, symmetric, and transitive if the corresponding relations R1 and R2 are reflexive, symmetric, transitive, respectively. So let's begin. So with 1, we know that R1 and R2 are reflexive, and we are being asked if the union is reflexive. And this is the wacky thing about relations. Because they are sets, we can take unions, we can take intersections, we can take set differences. And so all of a sudden, if we have relations, we can do one of these operations and then ask, what properties do the new sets, do the new relations have? And so here we are looking at unions. Now, we already know that a relation is reflexive if and only if it has the identity relation inside it. And so I'm going to use blue for scratch work. And so we know that in the premise, since R1 and R2 are reflexive, that tells us that the identity relation is a subset of R, and of R1, and the identity relation is a subset of R2. And so consequently, the identity relation is going to be a subset of the union of R1 and R2. And so that will take care of the first one. Now, for B, we want to see if R1 and R2 is going to be reflexive. So we can take an x, y in the union of R1 with R2. Now, by definition of the union, this means that x, y is in R1, or x, y is in R2. Now, we have two cases, but both cases are going to be essentially identical in terms of the write-up. And so if we do case 1, and this is where we're going to be using without loss of generality when we formally write this up, but just to emphasize this, if we do case 1, x, y is in R1, then because R1 is symmetric, we get that y, x is in R1. And then similarly, case 2, same situation. We have x, y is in R2, and this here will imply that y, x is in R2 by the assumption that R2 is symmetric. In the write-up, we can go ahead and use the phrase without loss of generality, which we introduced in the last lesson. And we can simply now say, without loss of generality, suppose that x, y is in R1. And then we do the argument here. And now this has the benefit that we do not have to break it into cases. So what about transitive? So now we're assuming that R1 and R2 are transitive, and we want to investigate the union. So to that end, let us go ahead and choose. And so let's see what happens. So let us choose some x, y and y, z in the union of R1 and R2. And since we want to show that it's transitive, what we are doing is choosing our arbitrary xy and yz to be in the union, and we want to show that x, z is in R. Okay, well, as before, this here is going to tell us that x, y is in R1, or x, y is in R2. And then similarly, we have y, z is in R1, or y, z is in R2. But this is a problem, because unlike the first case, where we established that it was symmetric by using the property that R1 and R2 were symmetric, we are in trouble with this situation, because what happens if x comma y is in R1 and y comma z is in R2? In that situation, we can't use the fact that R1 is transitive. Because of course, if it was the case that x comma y and y comma z were in R1, then we are done. Because R1 is transitive, x comma z is going to be in R1. Similarly, in the case where xy and yz are both in R2, we will be done because R2 is transitive, we get x comma z is in R2. But now, in this situation, where xy is in R1 and y comma z is in R2, we have no assumption to work with. So this is indicating that something is going to go wrong. And so with this in mind, let us construct a set that is transitive, a relation that is transitive for R1, and it has the property that this x comma y is going to be in that first relation, and then similarly a y comma z is in R2, but make it in such a way that the union does not contain x comma z. So let us consider the following. So let's go ahead and take A, and let's keep this simple. Let's look at 1, 2, 3. So that's our set for A. So let us take R1 to be the relation 1, 2. Now, is this relation transitive? Yes. And we have to come back to the definition, just as with the empty set. We only have one element. And the thing about the definition of transitive is that we need x comma y and y comma z. We need to have two elements, two ordered pairs, where the second entry in one ordered pair is the same as the first and the other. But since we only have one ordered pair, we never will have an ordered pair of the form 2 comma something appearing in R1. And so the premise for transitivity in the definition is false, and consequently we do have that R1 is true, since now the conditional is true, since we have a false premise. And so the set R1, 1, 2, it is transitive. If in the same manner we take R2, and now let's take this to be the set containing the pair 2, 3. By the same notion, these are both transitive. But now the union, R1 and R2, is going to be the relation with elements 1, 2 and 2, 3. And now this is not transitive, since 1, 3 is not in there. And so we are done. So we have the scratch work for this. And so this is the key, is that when we have a question like this, we don't know what the answer is from the start. And so what I did here was assume that we were going to go for the proof, but then keep an eye out for the irregularities. And what I mean by that is, can we use the assumptions always? As we saw with the transitivity here. We saw x comma y is in R1, y comma z is in R2. For that case, we couldn't mode the transitivity property to work there. And so rather, we made a counterexample that exploited this, where we had x comma y is in R1, and it is transitive, and then we also had y comma z is in R2. And so now we have that shared element 2 for both of these. So here is a formal write-up of the solution that we just went through. And so the one thing I want to point out is that in writing this up, so for example with reflexive, we have R1, and then I missed the R2 here. So we saw that it was reflexive. We used theorem 434, and that told us that because it's reflexive, the identity relation is in both R1 and R2. But then we also have to use theorem 434 again to go from the identity relation being a subset of R1 union R2 to deducing that R1 union R2 is reflexive. For symmetric, earlier in the scratch work, we did two cases, but they are identical. And so now, when we run through the argument, so we suppose R1 and R2 are symmetric, we choose our x, y in the union of R1 and R2, and then that tells us that, by definition, xy is in R1 or xy is in R2. But now, we can say, without loss of generality, we can suppose that x, y is in R1, and since R1 is symmetric, y, x is in R1, and consequently, y, x is in the union of R1 and R2. So I was missing that union over here, and that shows that R1 union R2 is symmetric. And finally, if we consider the set A consisting of 1, 2, and 3, we consider the following transitive relations, R1 and R2, and we give our counterexample, that the union is not transitive since 1, 2, and 2, 3 are in R1 union R2, but 1, 3 is not in R1 union R3. So the next exercise we're going to consider is 18. So here we have R and S are transitive relations on A. And we want to show that if S composed R is a subset of R composed S, then R composed S is transitive. And the way we are going to go about this is by taking our elements in the composition of R and S so we can apply the definition. So as a reminder, to show that something is transitive, we want to choose two elements, x, y, and y, z in that relation, and show that x, z is in that relation. So scratch work. So we're going to choose x, y, and y, z, some arbitrary elements in the composition of R with S. And we want to show that x, z is in the composition of R with S. And so that is the goal. So we got this. Now, how do we go from here to using the assumptions so that we can build our way up to what we want? And so the way we're going to go about that is by using the definition of composition. So x, y being in the composition of R with S tells us that there is some intermediary element. Let's go ahead and call it A in A, such that x, A is in S, and A, y is in R. And similarly, we also have the existence of some B in A, such that y, so now we're doing the same thing, but now to the y, z. So we have y, B is in S, and B, Z is in R. So we got our elements here, and so now we've just applied the definition of what it means to be in the composition. So where do we go from here? And so let's make the following note. We have over here a y and a y here. And so now we can apply the definition again for composition. Because what this is telling us is that because we have that a, y is in R, and y, b is in S, that the corresponding element a, b is in the composition S with R by definition. And so whenever we want to show something is in a composition, there must be some intermediary element, y, and then we drop the y in the ordered pair, and so now we have a, b is in S compose R. But now a, b being in the composition of S with R, now we can use the assumption that R compose S contains the composition S with R. And so now we have that this is telling us that A comma B is in the composition of R with S. And so we got this here. But now let us keep in mind what we want to do. What we want to show is that X comma Z is in the composition of R with S. We now have A comma B in the composition of R with S, but that doesn't seem to get us to where we want, because we need to somehow manage to get back the X and the Z. So what should we do? We've only used so far the definition of composition, but we have not used that R and S are transitive properties, are transitive relations. So what if we were to apply the definition of composition once more to A comma B? If we apply the definition again, then we have that the existence of some C in A such that A comma C is in S and C comma B is in R. And the reason that this is useful is that now we have A comma C is in S, but we also have X comma A is in S, and we know that S is transitive. So now we have X comma A comma C. These are both in S, and since S is transitive, we end up getting that X comma C is in S. Similarly, we have C comma B is in R, and if we come back to here, we have B comma Z is in R. And so we now use R as transitive, and we end up getting that now C comma Z is in R. But we got the missing link, because now we have the intermediary C that allows us to say that X comma Z is in the composition. And so these together, by definition, tells us that X comma Z is in the composition of R with S. And so we are done. And so this is a tricky question, because we had to apply the definition of composition several times. As a consequence, we ended up getting the existence of 3 different elements of A, B, and C. And each of those served in getting us the result. And so we are done with the scratch work for this. And so for the formal write-up, we have the following. And so here is the proof for the statement that we just did. And so we go through, state our assumptions. We start off by choosing our x, y, and y comma z in the composition of R and S. We use the definition of composition to deduce the existence of A and B, such that x comma A, y comma B are in S, and A comma Y, B comma Z are in R as ordered pairs. Now from this here, we make the observation that A comma B by definition is in the composition of S with R. And now the assumption of the containment tells us that A comma B is in R compose S. We use the definition of composition once more to deduce that the existence of some C such that A comma C is in S and C comma B is in R. And now we use the fact that S is transitive. And so in particular, A comma C, X comma A, they are in S. Transitivity then gives us X comma C is in S. And now similarly, C comma B and the ordered pair B comma Z being in R, now that implies that Z comma Z is in R. And so now we get X comma Z is in R compose S, which shows that the composition of R with S is transitive. And that finishes it off for this one.